hunch that some particular direction may work, so they try it. So so the approach we use here is we will calculate this and try to show that it is, this quantity here is in fact greater or equal to E naught, right? Now, as usual, whenever you have an expectation value, that value will depend on two things, right? I've said this before also. It depends on the operator, because you're finding the expectation value of the operator. And remember, expectation value is just another way of saying the average measured value, okay? In terms of laboratory results. And if you measured this observable, in this case it's the energy. Remember, the Hamiltonian is the energy operator. Okay. So if you are measuring the energy many times, get lots of statistics, and then you can calculate the average measured value. And by definition, that's the expectation value, which is this, right? And now so the operator. That's one thing, and the other thing is the wave function you're talking about. You have different wave functions. Of course, this quantity will depend on your choice of wave function. Okay, so well, we don't know. Let's assume we don't know what the true wave function is. So that's the whole point. We're guessing it. We're trying to estimate it. This is an approximation technique. It's this chapter, the whole chapter, the title of the chapter is Approximation Methods, isn't it? Yeah, Approximation Methods, chapter 10. Okay, so the variational method model. Let me just check. What is the term they use? Not that it really matters, but may as well be consistent with the text. Method. The variational method. Okay, so assume we don't know the real eigenfunction, so we're trying to approximate it, which is what this whole chapter is about. And the second major approach, the first being the perturbation theory approach, and the second one now that we're getting into the details of is the variational method. Okay, all right. Now, so the expectation value depends on the two things: the operator and the wave function. Now, we don't know what this wave function is, so let's assume that now it's effective in terms of the eigenfunctions of H. It's just some arbitrary wave function, right? So the wave functions, the eigenfunctions, the eigenstates, all the same thing, of the Hamiltonian operator, they form a complete orthonormal set. Remember, you've done that many times in the past. So let's expand this wave function, this trial function, this Ansatz, in terms of the eigenfunctions, eigenstates of H hat, right? So it would be of this form. Okay. Now, why do that? Well, if you have these in terms of the eigenfunctions of H, then you get eigenequation type terms, and you can then bring in, like, the right hand side of the eigenequation. You'll have an eigenvalue, but that's the energy, so you'll have En corresponding to this eigenstate Un. Okay? Now, you'll see in a minute what that happens. Okay, so let's here's part of the proof, the creativity of the proof. Let's rewrite this in terms of a weighted sum of the eigenfunctions of this operator, okay, of this form. And we also assume that the Ansatz trial function is normalized, okay? And that implies that the sum of the squares of these parameters, these coefficients here, is 1. Okay, so sigma an squared is 1. Okay, all right. Plug this into your expectation value, So this, and this is just shorthand for this, right? This is where this angular bracket, I've said this before, this angular bracket notation for the expectation value, you know, the average measured value, is just shorthand for this, right? And this is your bra-ket or bra-operated-ket notation from the Dirac notation. You know, we've done that before, right? So just take this and plug it into here and here. But this, by definition, is this is the overlap integral, okay? With your conjugate here. So plugging this into here gives you this in this term. So you know everything's conjugated, right? All the i's become minus i's. H bar as usual, and you know this is just this. All right. Now you can rearrange terms a bit. Now these coefficients here, these a's, are assumed to be not functions of the volume, xyz, whatever. It depends on the context of your problem. It might be one-dimensional, might be three-dimensional. Later in the next session, well, in fact, in this session and the next, when we do examples of this variational method, this here will be one-dimensional. Keep it simple, so we can just write dx. Right. So effectively, these have independent of x or the volume. So you know they can come outside. So the double sum comes outside. So you just get this, and then you're left with integral un star h hat un. Now these un perhaps I should mention. So this summation are independent. So let's just label the summing term with a different label. So here we've got n, and here we have m. You notice I emphasize the difference because if I'm not clear, in English m and n sound almost the same. So it's one of the disadvantages of the English language on videotape. It's no tape anymore, is it? It's like on video. Alright, so here, these are the eigenfunctions of this operator. So this here is like the left-hand side of an eigenequation. So you can change this then, instead of operator eigenfunction, you can replace it with eigenvalue eigenfunction. And what is the eigenvalue for the h hat operator? Well, it's just the eigenenergy, right? So it's just it'll be em, the mth discrete quantized energy level, right? Em. So here it is here, em. Okay. So the em is a constant that can come outside like here, and then you're left with integral un star um dt. Well, these are eigenfunctions of the operator. They are orthonormal. So you've got integral un that will be a delta function, right? If n and m are equal, that'll just be 1. Orthonormal, right? Orthogonal and normalized. Orthonormal, right? So you just get em and delta, delta function, nm. So this whole thing is 0 if n and m are different, and but if n and m are equal, well, this delta here becomes 1. The m becomes n. One of the sigmas drops away, and you're just left with you're just left with the modulus of an squared en. Right? Okay, so this term here, go back through the chain of logic. This term here is the expectation value for the Hamiltonian. Right? This equals this equals this equals this equals this. Right? So this term here is the expectation value of your Hamiltonian. Now, this is just a constant, right? It's an energy. It's a value. So you can bring this. No, wait a minute. Sorry, I'm getting ahead of myself. Now, we're trying to prove that the expectation value is greater or equal to the ground state energy E naught. Okay? Now, the fact that it's the ground state, that means, like,